So here are some examples of problems similar-ish to homework problems in order. So let's say we want to find, does the following sequence a sub n equal to 2n cubed plus 5n over 6n to the 7th plus 2n squared converge or diverge? So the fast way to answer this sort of question is, well, I guess I should say, if we're asking if something converges or diverges, we are really looking at the limit as n goes to infinity of it, or k if you're using k, but a lot of these uses n and more. So we're going to look at the limit as n goes to infinity of 2n cubed plus 5n over 6n to the 7th plus 2n squared. The shortcut answer is to just say the degree on top is smaller, so this thing converges to 0, or this thing's limit is 0. But the longer way of answering a question like this is to divide everything by the highest power of n in the denominator. So if we divide everything by n to the 7th, we get 2n cubed over n to the 7th plus 5n over n to the 7th plus 6 or over 6n to the 7th over n to the 7th plus 2n squared over n to the 7th. And then if we simplify that, we get the limit as n goes to infinity of 2 over n to the 4th plus 5 over n to the 6th over 6 plus 2 over n to the 5th. And you can see that all these things that are constants divided by powers of n are just going to go to 0. So we're left with 0 over 6, which is 0. On the other hand, so if we instead ask about something that looks like this, say a sub n equal to, let's actually just flip it over and say, let's change it up. We've got 3n to the 5th plus 4n over, I don't know, 2n cubed plus 5n plus 1. Here, we can make the same sort of conclusion, but now we see that the top is actually bigger, getting bigger faster. So we can say, oh, since the degree on top is bigger than the degree on the bottom, this limit's going to be infinity. Or we could do the same sort of work. We can divide the top and the bottom by the highest power of n that's in the denominator. So in this case, I'm going to divide everything by n cubed. And I'm going to get the limit as n goes to infinity of, let's see, I'm just going to do it and not just show all the work. So I'm going to say, if I divide everything by n cubed, and you get 3n squared plus 4 over n squared over 2 plus 5 over n squared plus 1 over n cubed. And then just like before, all the things that are being divided by n to a power are going to go to 0. So you're going to end up getting 3 times something infinitely large plus 0 over 2 plus 0 plus 0. 3 times infinity is infinity, divided by 2, still infinity. So this sequence diverges. And you can specifically say to infinity if you wanted to. Whereas this one here, I should have said, although, right, when you're saying a sequence, or the limit of a sequence is the number, or the limit of a series is a number, you are saying it converges to that number. So we would say that this sequence converges to 0. Cool. Stop me if you have questions. Looking at something similar. So, and then the third kind of situation is when the degree on the top and the degree on the bottom are the same. So if I said my sequence looked like, I don't know, 4n cubed plus 5n squared plus 1 over 6n cubed plus 7n minus 3. I don't like minus, plus 3. Again, if I was asking what this converged to, the shortcut answer would be say, oh, the degree on the top and the degree on the bottom are the same, so the limit's going to be 4/6. Or you can show the work. The limit as n goes to infinity of 4n cubed plus 5n squared plus 1 over 6n cubed plus 7n plus 3. The work, which I'm going to skip for a second, we would do, and the answer eventually is going to be 4/6, which reduces to 2/3. And the step I didn't show yet is to divide everything by the highest power of n that's in your denominator, which is going to be n cubed. So we get the limit as n goes to infinity of 4 plus 5 over n plus 1 over n cubed over 6 plus 7 over n squared plus 3 over n cubed. And then just like before, all these things that are being divided by powers of n go to 0, and you exactly get 4/6, which is 2/3.
So I thought that was just the end.
So you are right. All of these questions, if I was being asked about the convergence of the series, I could say, so just kind of for all of these, we could say that the sum from n equals 1 to infinity of this sequence, 4n cubed plus 5n squared plus 1 over 6n cubed plus 7n plus 3, this definitely diverges by the nth term test. But if you're looking at question 1 or 2 on your homework assignment, they're specifically asking about the convergence of the sequence. So this sequence, 4n cubed plus 5n squared plus 1 over 6n cubed plus 7n plus 3, converges to 2/3. And because of that, the series of that sequence would diverge by the nth term test. In a similar way, from the previous page, we could also say that this series, so the sum from n equals 1 to infinity of 3n to the 5th plus 4n over 2n cubed plus 5n plus 1 also diverges by the nth term test, because its sequence does not converge to 0. On the other hand, the first sequence we looked at, 2n cubed plus 5n over 6n to the 7th plus 2n squared, we could not say that the series for that diverges by the nth term test. So this series, sum from n equals 1 to infinity of 2n cubed plus 5n over 6n to the 7th plus 2n squared, nth term test tells us nothing. Because the limit of the sequence is 0. If you were going to try and show that that series converge or diverge, typically when you have, what am I saying here? When you have things that look like or rational functions, typically the way you want to show convergence or divergence is by appealing to the limit comparison test. So here I would observe that 2n cubed n cubed is the highest power on top, n to the 7th is the highest power on the bottom. So I would limit compare this to the sum from n equals 1 to infinity of n cubed over n to the 7th, aka the p series 1 over n to the 4th. So I'm looking for convergence because I'm comparing it to something I know converges. And it would show convergence, right? If we do this, the limit as n goes to infinity of the unknown 2n cubed plus 5n over 6n to the 7th plus 2n squared divided by the known or multiplied by the reciprocal. We're going to be getting the limit as n goes to infinity of 2n to the 7th plus 5n to the 4th, n to the 5th over 6n to the 7th plus 2n squared. And again, using that same trick that if we've got the same degree, the limit is just the quotient of the leading coefficients. That's going to equal to 6, which reduces to 1/3, and that's not 0 or infinity, so we're good to go. Since this series converges, this series also converges. So this series converges by limit comparison with this convergent p series. Let's look at this next question. So this next question is similar-ish to problem 3. This one we kind of talked about last time, but I wanted to do another example just because I saw someone ask about it on whatever was it, Piazza, yeah, like what is Reddit, Piazza, whatever it is, yeah. So let's look at this. Limit is n goes to infinity of 2n factorial over -3 to the n. Now, well, again, we're just looking at the sequence. We're not asking about the series. So we couldn't really use the ratio test here, although I'm gonna use it just to talk about something anyway. So let's pretend like we did the wrong thing and we used the ratio test. But again, I will point out that the ratio test, at least in this class, is only for series or sums, not just sequences. Well, let's say we did it anyway. So I do the limit as n goes to infinity of an plus 1 over an I'm actually going to ignore the absolute values that often live there because like I want to see something. I know what I want to see. That's why I'm doing this. So if we do this, we get the limit as n goes to infinity. Let's see. So I get 2 times n plus 1 factorial over -3 to the n plus 1 times the reciprocal of the original thing, which is -3 to the n over 2n factorial. We've had some practice with factorials. We know that this is going to be 2n plus 2 factorial, which is, and we're going to group things together. So we're going to have the limit as n goes to infinity of 2n plus 2 factorial over 2n factorial. We have to group the like things together. And then we have a -3 to the n over -3 to the n plus 1. Simplify it a bit. Limit n goes to infinity of, let's see, so 2n plus 2 factorial is 2n plus 2 times 2n plus 1 times 2n times 2n minus 1 times 2n minus 2 times, which is just your 2n factorial over 2n factorial. And those are going to cancel each other out. And then we also have the -3 to the n over -3 to the n plus 1 is going to be a 1 over -3. So before I evaluate some, I just want to rewrite it one more time. Again, the limit n goes to infinity of 2n plus 2 times 2n plus 1 over -3, which is, that limit's going to be what? Right. But specifically, and I do want to be specific here for a second, it is infinity divided by a negative number, which makes it negative infinity. So remember what the ratio test is actually telling us. What we're saying is this sequence, if you write out a bunch of terms, eventually each subsequent term looks like the previous term multiplied by the ratio. So let's say we wrote out some terms. I'm just going to, so a sub n, here's some terms. So the first term is, right, so it's going to be, let's see, 2 factorial over -3. And then the next term is going to be 4 factorial over -3 squared. And then the next term is going to be 6 factorial over -3 cubed. So we can see that, right? So far it's like, okay, whatever. But then if we go way out to like the 100th term, you're going to get 200 factorial, which is really big, like super freaking big, over -3 to the 100th power, which is also big, but not nearly as big. So I've got a really large positive number over a not quite as large positive number. So this number is really very positive. But then the next number is 202 factorial over -3 to the 101, which is very negative. So the problem here is that this sequence definitely is diverging, right? The top thing is a much bigger thing than the bottom thing that's also big. Right? We talked about last time how factorials are always going to outpace exponentials. But we're bouncing back and forth between ever more positive and ever more negative. So although this diverges, it diverges in a way where we can't say it diverges to positive infinity or to negative infinity. We are stuck with saying it only diverges. So even though the ratio test doesn't really tell us about the behavior of the sequence, it does in some sense. You're saying, oh, each next term is going to be a much larger but negative multiple of the previous term. So if this thing was big and positive, the next thing's a lot bigger and negative. The next thing's a lot bigger and positive. And so you're bouncing back and forth. Or you can do the thing we kind of did last time, but again, evaluating this limit is not particularly easy. It requires writing out a bunch of terms, kind of breaking things apart. It's a lot simpler to say, I know the top thing's bigger, but since we're alternating signs, I know that the limit doesn't equal negative or positive. Now, if that bottom thing were just 3 to the n, it would totally be fine to say that the limit was positive infinity. Okay. We did some telescoping sums last time. Let me do one more example. I was going to do, so I feel like the number 4 is pretty straightforward. You can just write out some terms and most of the stuff cancels. 5 is a little trickier, so let's do one kind of similar to 5. So let's say we want to find, and again, it's important to really read the question, right? So like for number 4, it says determine whether the series is convergent or divergent, and then if it is convergent, find its sum. We can tell it's convergent. Well, I don't know. How could you tell it's convergent, actually? Good question. I guess we could break it up. So that first one, so we could break that first one up into two sums. Like, so just for everyone who's watching this later, this example 4, which in my notes looks like this, 3 over k minus 1 squared minus 3 over k squared. If you were just being asked about whether or not this converges and not what it converges to, you could totally rewrite it as just the sum from k equals 3 to infinity of 3 over k minus 1 squared minus the sum from k equals 3 to infinity of 3 over k squared. And both of these are convergent by limit comparison with a p-series. So you could totally do limit compare with the sum of 1 over k squared. Same deal here. Limit compare with the sum of 1 over k squared. And since those are both convergent, and this limit comparison will result in getting the same behavior, each of these converge and their sum or difference also converges. And then you can start writing out terms. But really the way you would actually do this is you just start writing out terms and be like, oh yeah, the things cancel. I'm left with the first term. The last term that's left over there in the partial sum goes to 0. So we're safe. But let's look at the next one, which is giving us, I'm going to do something like, let's find the sum from n equals 2 to infinity of 8 over n minus 1 times n plus 2. So first and foremost, if this question only said to determine whether or not it converges, I wouldn't do what I'm about to do. So if I was just looking for convergence or divergence, I would say, well, look, this thing looks like the sum from n equals 2 to infinity of 8 over n squared minus n plus 2n is plus n minus 2. And then I would just do limit comparison. I would say, okay, great. Limit compare with this. And then I'm going to say, okay, well, the limit as n goes to infinity of the unknown thing over the known thing. Well, that's going to be the limit as n goes to infinity of 8n squared over n squared plus n minus 2. And what's that limit? 8. And 8 is not 0 and it's not infinity. So if whatever this does, that also does. And since this is certainly convergent as a p-series, this also converges by limit comparison. But that's not what we're being asked. We're specifically being asked in this problem to determine the sum of the series if possible. And so I guess, I mean, technically they could give you something that diverges, but they give you a hint just to use partial fractions. So we're going to do the partial fraction decomposition here and say that 8 over n minus 1 times n plus 2 is equal to a over n minus 1 plus b over n plus 2. The nice things about these telescoping series that have a partial fraction decomposition is they're always going to be nice. It's always going to work out. We just get to pick nice numbers to plug in and solve for a and b. First, we're going to multiply both sides by the common denominator, just like we always have done with partial fractions. When we do that, we get 8 on the left. We get a times n plus 2 plus b times n minus 1. We pick nice values of n. I'm going to pick n equal to 1. We're going to get 8 equal to a times 3. So a is going to be 8 thirds. And for this to really have a shot at working, it better end up being the case that b is the opposite sign of a. Otherwise, this just won't work. So if we plug in n equal to -2, we get 8 equal to a times 0 plus b times -3. So yes, we do get b equal to -8 thirds as we need it to be. Here's what we've really got. Our sum can be rewritten as the sum from n equals 2 to infinity of a, which is 8 thirds over n minus 1 minus 8 thirds over n plus 2. The only other thing you really need to look out for here is how many terms are we actually going to need to add together? Well, what's the difference between n minus 1 and n plus 2? Right. Literally, if you subtract them, n plus 2 minus n minus 1, the n's cancel and you get 2 minus minus 1, which is 3, which means we're going to need 3 terms. You'll see it if you write it out, but it's good to know what to expect. So we start writing things out. We're going to get, and here's what I'm probably get a little messy. So I'm starting with n equals 2. So we get 8 thirds over 1 minus 8 thirds over 4. I do recommend writing each term in parentheses. So this minus this plus, then we're going to get, now each of the denominators is just going to increase by 1 every time. So I'm going to get 8/3 over 2 minus 8/3 over 5 plus 8/3 over 3 minus 8/3 over 6. If you prefer, like a scroll in the room. If you prefer, you could have factored out the 8/3 from the beginning. I didn't. So there's my first 3 terms where nothing cancels. And then finally, when I write the 4th term, 8/3 over 4 minus 8/3 over 7, that's when things start to cancel. The 8/3 over 4 cancels with the negative 8/3 over 4. And then my next term would have an 8/3 over 5, which would cancel this negative 8/3 over 5. Then my next term would have an 8/3 over 6, which would cancel this negative 8/3 over 6. And then the next term would have an 8/3 over 7, which would cancel this, right? All the things start to cancel after you get there. So we're left with just 8/3 times 1 plus 1/2 plus 1/3, which you could simplify if you wanted to, but I don't think we need to really. Fine, we could. 8/3 times 6/6 plus 3/6 plus 2/6 ends up being what? 11/6. So we get 88 over 3 times 6, which is sure 44 over 9. Lovely, lovely answer. Okay. Now we're getting to the meat of things. Cool. So again, be very, very aware of the difference between asking whether a sequence converges or diverges and a series converges or diverges. Sequence, you're just taking the limit of the sequence, and whatever number you get, that's what it converges to. Or if you get infinity or negative infinity or some sort of back and forth thing, that's when it diverges. Series, on the other hand, a little more complicated. Let's look at this next example that's similar-ish to number 6. Let's see if we want to find the. So I'll point out the way 6 is phrased leaves no room for any guessing. It says, determine the sum of the following series, which means they are telling us already it converges. So determine the sum. What have I made up here? The sum from n equals 2 to infinity of -4 to the n minus 1 over 5 to the n. So pro tip, if they've told you to find the sum of a thing, it's got to be one of 2 types of things. It's either a telescoping series like we just saw, or it's a geometric series. Those are the only things we are capable of finding what they add up to, typically. And yes, there are other examples which you can work hard to, but usually in any calculus class, the only types of things they're generally expected to find the sum of are telescoping series and geometric series. So here, you can either start writing out terms, and I kind of like writing out terms, not going to lie. The first term is going to be -4 over 5 squared. The next term is going to be -4 squared over 5 cubed. The next term is going to be -4 cubed over 5 to the 4th. That makes it really, really easy to see what the ratio is. Every time to get from here to the next term, I'm just multiplying by -4 over 5. -4 over 5. So one way to do this would be to write it that way and say, okay, great. That means this is going to add up to the first term, which is -4 over 5 squared over 1 minus the ratio. And I really, really can't recommend enough doing it any other way. I find this just to be the easiest. On the other hand, maybe you don't like writing out these terms. So alternatively, you can re-express this as as something where you have some number times your ratio to the nth power. And that kind of involves breaking apart anything raised to the nth power plus or minus something else and pulling off the plus or minus piece. So I'm going to rewrite this as the sum from n equals 2 to infinity of, I have a -4 to the n times a -4 to the -1. So I'm going to rewrite that as -4 to the -1, and then the -4 to the n over 5 to the n, I can re-express as the sum from n equals 2 to infinity of -4 over 5, -4 to the n over 5 to the n. I'm just going to write as the fraction -4 fifths to the n. And then -4 to the -1, I am going to rewrite as 1 over -4. But then it's still going to be the first term over my ratio. My ratio is -4/5, because that's what's being raised to the nth power. So this is going to equal the first term, which is what I get when I plug in n equals 2. So I'm going to get -1/4 times -4/5 squared over 1 minus my ratio, which is the same as what I have up here. It looks slightly different, but it's the same. And then I should, at least I think I should simplify this. So I'm going to simplify a bit. I have -1/4 times +16 over 25 divided by 1 plus 4/5 is 9/5. And I'm going to flip and multiply. So I'm going to get -1/4 times 16 over 25 times 5 over 9. And then cancel some stuff. Cancel a 4 here. Cancel a 5 here. And I'm left with -4 on top. And 5 times 9 is 45 on the bottom. And yes, it's totally possible for your sum to add to something negative if your first term is negative, right? Because essentially this is the biggest thing, and then you're adding a slightly less or a slightly smaller positive thing and subtracting off a slightly smaller negative thing. So you're never going to escape the negativeness if you start with a negative number. Totally fine. Yeah, cool. Let's look at, I feel like 7, something similar to 7 is an easier question personally. If I had something like, well, actually, let me ask, let's do 2 versions of this. Let's do the sum from n equals 1 to infinity of 7 over 3 to the n. So first things first, converge or diverge? Well, what kind of series is this? Is it geometric? It might be easier to tell if we break apart the pieces. I write this as the sum from n equals 1 to infinity of 7 times 1 over 3 to the n, or preferably the sum from n equals 1 to infinity of 7 times 1/3 to the n. Then it's a little easier to see that it's geometric. But if you don't like this or find this just more challenging, just write out terms. Really writing out terms, although it feels kind of rudimentary, it really makes it easy to tell if it's geometric or not. So if I start writing out terms, my first term is 7 over 3. Then my next term is 7 over 3 squared. And then my next term is 7 over 3 cubed. The next term is 7 over 3 to the 4th. Oh yeah, every time I'm just multiplying by 1/3. It's totally a geometric series. So it's geometric, and my ratio is a number that's smaller than 1, meaning we're going to get convergence. Or I should say a number that's between -1 and 1, right? My ratio, which is 1/3, its absolute value is between 1, or is less than 1, I should say. So yeah, this is going to converge, and it's going to converge to the first term, 7/3 over 1 minus the first, or the ratio, which is 7/3 over 2/3. You can either flip multiply or just see that the denominators cancel and get 7/2. So yeah, when you basically just have something to the n and no other instances of n, or k if you're using k, as long as you just have an n in the exponent like that, it's going to be geometric. And your job is just to determine what the ratio is. And again, I've had so much practice with this, I prefer to kind of do it like this because it just looks nicer to me. But honestly, writing out terms is probably the easier way to figure out what the ratio is. It takes a little bit of effort, but it's not too much effort. Let's look at a similar problem. Let's say I had a sum from n equals 1 to infinity of, sure, let's see, how do I use, yeah, let's say I had 2 to the 2n plus 1 over 5 times 3 to the n. I like that. It's good. So again, this is still similar-ish to problem number 7. What I would say about this is it definitely looks geometric to me because I see only things raised to powers of n. I don't see an n factorial. I don't see like just n squared or n cubed or anything like that. All I see is powers of n. I think it's geometric, so my job is to figure out what the ratio is. oh yeah, something to be careful about. 5 times 3 to the n is not 15 to the n. Right, we just have to leave it as 5 times 3 to the n. So it's probably easiest just to start writing out terms. So let's see, the first term, if n equals 1, I get 2 to the third over 5 times 3. And then the next term is going to be, so if I plug in n equals 2, I'm going to get 2 to the fifth over 5 times 3 squared. I like to write out at least 3 terms just to kind of to make sure I'm not like doing something silly, but the next term, you can start seeing the pattern of the powers, right? The next power for 2 is going to be 7. The next power for 3 is going to be 3. So every time to get from one term to the next term, I'm multiplying by a fraction. And what number am I multiplying by on the top? Right. And on the bottom? Right. That's bigger than 1, which is fine. Right. Like if we were asked what if this is a geometric series, the answer is yes, it's a geometric series, but our R is 4/3, which is bigger than 1, which means this series is going to diverge. This geometric series diverges. You could also have done the other thing that I like to do where you rewrite it as the sum from n equals 1 to infinity of 2 to the 2n times 2 to the 1 over 3 to the n times 5, and then see that this is really the sum from n equals 1 to infinity. 2 to the 2n is 2 squared to the n, which is 4 to the n. And 4 to the n over 3 to the n is 4/3 to the n. And then you'd be like, oh yeah, my ratio is 4/3, and that means divergence for a geometry series. Cool. I did one like 8 last time. 8's pretty simple. You're just splitting it up into 2 things. So if you see something like this, well, actually, I should do one similarly. So for example, if I had this series from n equals, 1 to infinity of, what have I got here? Yeah, sure. 3 to the n plus 4 to the n over 6 to the n. It's not super obvious this converges right away. And if you start writing out terms, it's not going to be obviously geometric because it's not actually geometric. It's 2 geometric series added together. So the idea here is to break this apart as the sum from n equals 1 to infinity of 3 to the n over 6 to the n plus the sum from n equals 1 to infinity of 4 to the n over 6 to the n. Is this first part convergent or divergent? Right, what's the ratio here? Sure. How about here? Is this convergent or divergent? Right, and the ratio is 2/3. So you can find what each of these add to, and I think you are asked to find what they each add to. Yep, determine the sum. On the other hand, if my series was the series from say like n equals 1 to infinity of 8 to the n plus 5 to the n over 6 to the n, I would still break it apart and write it as the sum from n equals 1 to infinity of 8/6 to the n plus the sum from n equals 1 to infinity of 5/6 to the n. But then, even though this series over here would converge, because your ratio is 5/6, this first series would diverge because your ratio is 4/3. Once one piece diverges, the whole thing diverges, which is a good lesson to learn, right? Very, I should say, infinite series have a lot of things in common with improper integrals. So just like with improper integrals, when one piece diverges, the whole thing diverges. With infinite series, if one piece diverges, the whole thing diverges. Cool. Oh yeah, that's good. So let's talk about limit comparison for just a second, because limit comparison, at least for problems 9 and 10, I think is really kind of easy to apply. So when you're faced with something rational, meaning, or I should say, not even just rational, any powers of n over any powers of n, and maybe I should say any positive powers of n. So it doesn't have to be rational, meaning it doesn't have to be positive integer powers. You can have kind of any fractional powers, or even kind of weird square roots of stuff or cube roots of stuff. So here's what I would say. If I'm looking at something like, so this is like 9 and 10. If I have something like the sum from n equals, I don't really care where I'm starting, 1 to infinity of, oh, I should do, yeah, let me be a little extra thoughtful here just for a second. Sure, that's good, yeah. 7n squared plus 5n plus 1 over, yeah, sure. Let's say 2n to the 5th plus 4n squared plus 2. So if I want to know if this converges or diverges, and what you should be looking at if you have just powers of n, or even if they're in fractional powers, is you're just looking at the highest power on the top and the bottom. That's always the deciding factor. So then I know based on that, I'm going to limit compare with the series from n equals 1 to infinity of just n squared divided by n to the 5th. That is always the rationale, which is just the series from n equals 1 to infinity of 1 over n cubed. And I know that that series is convergent or divergent. Right, this is a convergent P series. So when you're dealing with something like this, you're always just trying to compare it to some sort of P series that you get by taking the highest power of n divided by the highest power of n and then reducing it to whatever makes sense to reduce it to. So then, and the thing is, this process becomes just the same work every time. You're going to dividing this by that, you're going to flip and multiply, which is going to change the highest power on top to being the same as the highest power on the bottom. So when we do this work, the limit as n goes to infinity of 7n squared plus 5n plus 1 over 2n to the 5th plus 4n squared plus 2. I wouldn't normally write this part like this. I would normally just jump to flipping and multiplying and say, oh yeah, that's going to be the limit as n goes to infinity of 7n squared plus 5n plus 1 over 2n to the 5th plus 4n squared plus 2 times n cubed over 1, which I really have written too many things for this problem. We got the limit as n goes to infinity of 7n to the 5th plus 5n to the 4th plus n cubed over 2n to the 5th plus 4n squared plus 2. And when we're taking this sort of limit, you can show more work if you want, but I really encourage you just to come from the, oh yeah, highest power on top, or the degrees are the same. So the limit's just the quotient of those leading coefficients, which is going to be 7/2. And since that number is not 0 and not infinity, these both have the same behavior. So since this converges, that also converges. But it's always going to be whatever this one's doing. So, right, either you're going to get the same behavior or an inconclusive test. Let's look at 2 more examples. Let's say I want to do the sum from n equals 1 to infinity. Maybe more than 2 more examples. All those are, that is interesting. Sorry, I see me. Okay, so I will point out that in problem 10, especially, your powers of n are written out of order. It's in your interest to either, I mean, you don't have to write them in order, but to just see where the highest power is. So I guess I'll try and do one that's kind of like that just to be annoying. So let's say we have the sum from n equals 1 to infinity of, sure, let's do 6n squared plus 5n cubed plus 8n to the 4th over 2n plus 3n to the 5th plus 6n squared. How annoying. So someone will write it like this. Okay, so again, we're just looking for the highest powers of n in each spot. So I see an n to the 4th on the top. I see an n to the 5th on the bottom. So we're going to limit compare with the sum from n equals 1 to infinity of n to the 4th over n to the 5th, which is the sum from n equals 1 to infinity of 1 over n, which we know is divergent. So we are looking to test for divergence. We can't come up with any other result other than either divergence or inclusive. Now I should tell you also that when you're dealing with rational functions like this, the limit comparison test is never inconclusive if you compare it to the right thing. Meaning if you just use the highest powers like what we're doing, you will always get a conclusive result, which is nice. So then we're going to do the limit as n goes to infinity of the unknown thing, which I personally would rewrite in the correct way, or the standard way I should say, not correct, standard, of 8n to the fourth plus 5n cubed plus 6n squared over 3n to the fifth plus 6n squared plus 2n times, right, I'm not going to divide by 1 over n, I'm going to multiply by n over 1. And then we can see that if we distribute this n, we're going to get exactly what we thought we should get. 8n to the fifth plus 5n to the fourth plus 6n cubed over 3n to the fifth plus 6n squared plus 2n. And that's going to equal 8/3, which is not 0, not infinity. So same behavior. So we get divergence. I'll point out, it doesn't matter if this number is bigger than 1 or less than 1, right? We're not doing a p-series. We're not doing a ratio test where it matters if it's bigger than 1 for divergence or less than 1 for convergence. Or I should say, for a ratio test, bigger than 1 diverges, less than 1 converges. For the p-series, opposite of that, bigger than 1 converges, less than or equal to 1 diverges. But here, it doesn't matter what number you get. It just matters that it's not 0, not infinity. And then the behaviors are the same. Meaning if you compare to something convergent, you get convergence. If you compare to something divergent, you get divergence. Let's look at one more example because I want to just see one more thing. Yeah, let's say, I don't love that, but that's fine. Two more examples. Sorry, I keep saying one more. I mean, it's always one more example until class is over. One more example. So let's look at this. The sum from n equals 1 to infinity of n squared plus 2 over the square root of n to the fourth plus 3. Now here, you can't really, what am I trying to say here? What am I trying to say? It's not a rational function, but you can still use the limit comparison test as if it was. So actually, but I'll say here, you don't even have to use limit comparison test. So technically, if you wanted to, you could say, well, I'm going to limit compare this to the sum of what's my highest power on the top. And kind of, not exactly, but essentially, what is my highest power on the bottom? Right. Which that looks like it's just 1, which might lead me to think maybe I should be thinking of the nth term test before I even try limit comparison. Because my highest power on the top and the bottom are kind of the same. I probably just use the nth term test. And I can. If I do the nth term test, if I do the limit as n goes to infinity of the sequence, there's a couple ways of dealing with this. I personally have always liked to deal with this by essentially just dividing out that highest power of n in the square root. So I'm going to rewrite this as the limit as n goes to infinity of n squared plus 2 over the square root of n to the fourth times 1 plus 3 over n to the fourth. The reason is so that I can bring out the n squared. Because what's the square root of n to the fourth? It's n to the fourth to the 1/2 of n squared. This is going to be the limit as n goes to infinity of n squared plus 2 over n squared times the square root of 1 plus 3 over n to the fourth. And then you can either justify to yourself that the highest power on top and the bottom are the same. So you're going to get 1. Or if you want to do one more step, you can divide everything on the top and bottom by the highest power. So I do that, which I think is probably worth doing just to see it. I'm going to get n squared over n squared plus 2 over n squared over this whole thing, right? Because this is a product. We don't divide each piece by n squared. We just divide the whole thing by n squared. So here we end up getting the limit as n goes to infinity of 1 plus 2 over n squared over the square root of 1 plus 3 over n to the fourth. And then just like every other time, that goes to 0, that goes to 0, you end up with 1. Which is not 0, right? Because we were doing the nth term test here, which means the series diverges. Let's look at one that's similar to this, but doesn't go the same way. Let's say we wanted to look at the sum from n equals 1 to infinity. Where'd you go? Of, sure, n squared plus 1 over the square root of n to the 6 plus 2. Now I am going to limit compare it. I'm going to limit compare it with, well, what should I have on top? N squared. And what do I essentially have on the bottom? Right. So I'm limit comparing with something that's divergent. And then the work's going to be the same. Or not the same. The usual work for limit comparison. It's going to be the limit as n goes to infinity of the unknown over the known. So n squared plus 1 over the square root of n to the 6 plus 2 times n over 1, which is going to be the limit as n goes to infinity of n cubed plus n over. I can do the same sort of work I did before. You can do kind of as much as a little work here as you feel like you need to. You might convince yourself it's just, well, I've got a 1n cubed on top and essentially a 1n cubed on the bottom, so the limit's going to be 1 over 1. If you don't like that, you can do the thing where you factor out the n to the 6th. And then the square root of n to the 6th is n to the 3rd. So this really becomes the limit as n goes to infinity of n to the 3rd plus n over n to the 3rd times the square root of, I don't know why I put the parentheses there, 1 plus 2 over n to the 6th. And then just like last time, we can divide everything by the highest power of n. Or you can just say, I've got a 1n cubed over 1n cubed, which is 1 over 1. But if you want to do the division, the limit as n goes to infinity of 1 plus 1 over n squared over 1 times the square root of 1 plus 2 over n to the 6th. And just like before, that goes to 0, that goes to 0. So this limit is equal to 1. Now, we're not saying this diverges by the nth term test because we didn't take the limit of the sequence. The limit of the sequence would be 0. But the limit comparison test tells us that both this series, which diverges, and this series have the same behavior because your limit was not 0 and not infinity. So also diverges. Okay, got 4-ish minutes left. So before I keep talking, that basically covers the first 10-ish questions of the homework. Like that, you should be able to find some similarity between those first 10 problems and anything we've done here. Are there any of the last 1, 2, 3, 4 questions that you specifically have questions about? I will just point out while you look that for question 13, the sum of from n equals 1 to infinity, I'm going to change it to a different, like of 1 over n to the 6th, definitely converges, as you all know as it's a p series, but it definitely cannot be shown to converge by the ratio test. So if you try using the ratio test, you're going to get the limit as n goes to infinity of 1 over n plus 1 to the 6th over 1 over n to the 6th, which is going to be the limit as n goes to infinity of n over n plus 1 to the 6th, which is just 1 to the 6th, which is 1, which is inconclusive. So even though that series converges, we have to say that 13 is false because you can't show that a p series converges by the ratio test. Okay, go ahead, Reed. Or if you have things you want me to address.
14 looks monstrous.
Okay, so use the ratio test to, I'm just sorry, I got stuck looking at 11 there for a second. So 14 says use the ratio test to determine whether this thing converges or diverges. So I'll make up something slightly different. Oh, I was like, why are we starting at 21? That's why, because it starts at 21. The sum from, sure, n equals, I don't know why they started at 21, but they have. Who knows? I'm gonna change it up just a little bit. Let's make it n squared times negative 7 to the n over n factorial. I'll point out that when you're using the ratio test, n to a power literally is inconsequential. So let's think about this, right? If I deal with the ratio test for this, let's just write it out. So ratio test time, right? Because that's what they get. So ratio test. And I'm not exactly sure what they're asking you to do for part A here. So find the ratio of successive terms, write your answer as a fully simplified fraction. Okay, I think I know what they're getting at there. So if I start taking the limit as n goes to infinity of this expression, of an plus 1 over an. in absolute value. Ooh, in absolute value. Interesting. 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 Okay. So we're going to get a limit as n goes to infinity of n plus 1 squared times negative 7 to the n plus 1 over n plus 1 factorial. Oh, neat. Aha, I see. Mine's going to turn out not quite as nice as theirs is going to because I made an n squared. That's all right. And then flip it, n factorial over n squared times negative 7 to the n. Now let's group some like terms. So let's see. So I'm gonna group these like terms. I'm not gonna put them together exactly. I'll point out we have n plus 1 squared over n squared. And I'm just gonna tell you, right, if I took that limit, although we're not taking it yet, what would the limit of that part be? Sure. Or even just n plus 1 squared over n squared is n squared plus, I don't actually care, but I'm going to write out the lower terms. Right? That thing has the usual rational function deal where, yeah, so really, it wouldn't matter if this was cubed, 4th, 10th, 1000th power, n plus 1 to the 1000th over n to the 1000th. If you let n go to the infinity, the only thing that really matters is that first term when you multiply it out, and that's just going to be n to the whatever your power is. So this part's kind of inconsequential. It does matter in this problem because we have to do the simplifying, but normally I would just be like, oh yeah, that's going to go to 1. So then I'm going to have my n factorial over n plus 1 factorial, which we know reduces to just 1 over n plus 1, right? That's what typically happens. And then finally, we have our negative 7 to the n plus 1 over negative 7 to the n. Okay, so let's simplify. I'm going to leave this as is, although normally I would write n plus 1 squared over n squared as n plus 1 over n quantity squared. But that's not going to be helpful yet. The limit as n goes to infinity of the absolute value of n plus 1 squared over n squared times 1 over n plus 1 times negative 7 to the n plus 1 over negative 7 to the n is just negative 7. And then the last two simplifications we can do is we can cancel one of the n plus 1s. Now in your problem where it's just n plus 1 over n, the n plus 1 will cancel and you'll be left with just a 1 over n. And then I'm going to write this as the limit as n goes to infinity of the absolute value of n plus 1 over n squared times negative 7. Now, I know n plus 1 over n squared is positive. So if I really wanted to fully simplify this, I think we should drop the absolute values and say, well, that's positive and the absolute value of negative 7 is 7. So I can really write this as 7 times n plus 1 over n squared. I should still be writing the limit. Because the absolute value of a product is just the product of the absolute values. The absolute value of n plus 1 over n squared is just n plus 1 over n squared. The absolute value of negative 7 is just 7. So that would be the answer-ish to something like part A, where they said fully simplify your limit until you get this. Now, if we actually take this limit, well, it's going to be 0 because the degree on top is less than the degree on the bottom, which we addressed at the very beginning of class today. So that's going to be 0. Which is good. Well, I'm not good. I mean, so good. I always feel like convergence is yay, divergence is boo. Like, so I'm always like, yay, convergence or boo, divergence. So when I get convergence, I'm like, that seems good. Whereas I often characterize divergence as bad. But that's, I mean, dumb, right? It doesn't really matter when we're there. So, but yes, this is 0, which is less than 1, which means we get convergence. Yeah, and that's it.